Hello my esteemed viewers. In this tutorial, the concept of volumetric stress, volumetric change and the bulk modulus will be clearly explained. Whenever an element or a component is subjected to the stresses along several directions, here along three mutually perpendicular directions, one along sigma x, the other stress along sigma y, another stress along sigma z. The dimensions along x will change owing to sigma x, and dimensions along z will also change due to sigma z and consequent strains, and sigma y will contribute for the changes in the dimensions that are stretched along y direction. So anyway, there will be overall changes in the original dimensions of the body or original dimensions of the component. Therefore, change in volume, however small it may be, will be imminent as far as application of loads are concerned, as far as the loads within elastic limit is concerned. And we can develop an expression as to how the volumetric change and let us say volumetric strain can be formulated, or there could be a formulation in terms of stresses, the elastic modulus and the Poisson's ratio. So Poisson's ratio will also come into effect. You consider the effect of sigma x. Sigma x is acting along x direction and it will create the strain which is called as primary strain along x direction. But anyway, the stresses acting in the other direction, say sigma z, will also affect on the dimensions along x. That means sigma x, which is a stretching stress or a tensile stress, will always reduce the dimensions along x direction. So it will lead to compression. And here again sigma y will also lead to compression along x direction, and this is side effect caused by sigma z and side effect caused by sigma y. And this side effect, as you very well understood, the side effect can be accommodated by the Poisson's effect, therefore in terms of Poisson's ratio. Therefore, whenever we attempt for obtaining an expression for volumetric strain and the consequent changes in the dimensions of the element, Poisson's ratio will be automatically included, and it goes without saying, of course. And this is the change that is going to happen. It may become big. The earlier cube or earlier rectangular element may become big depending on the kind of stresses acting in the three mutually perpendicular directions. So when a body is subjected to stresses acting in different directions, and the consequent changes in the dimensions will cause change in volume of the body, and this is the crux of the discussion. And this is the changed volume. Changed volume has gone for increase as far as this figure is concerned when compared to the original size of the element. Like other kinds of strains, volumetric strain may be defined as change in volume to the original volume. Volumetric strain is also called as dilation by some of the authors. So by going by this definition, volumetric strain is change in volume divided by original volume, and it will happen something like this. This was the original volume, and when the pressure is applied in the form of air, and this will have increased volume. This is what happens even in any material. As a matter of fact, of course, things are amenable only within elastic limits, and beyond elastic limit the entire course strength of materials cannot extend, and that is not our we delimit our discussions within elastic limits, because materials will tend to behave erratically or non-linearly when they cross elastic limits. Expression for volumetric strain we will obtain. Consider a element which is acted upon by sigma x along x direction, sigma y along y direction, and sigma z along z direction. So due to this sigma x, there will be a small change in the dimensions of x, along x, that is, it may be called as dx, and along y may be called as dy, and along z may be called as dz. So let dx, dy and dz be the small changes in the dimensions of the cube, in the dimensions of the cube, in the directions along x, y and z directions respectively. Yeah, the changed volume is, anyway, after application of whenever the loads come to play, the changed volume may be written as V, the original volume, plus changed volume. This is change in volume, original volume plus change in volume. It could be minus also, but anyway, for the sake of ease in our derivation, we will assume that it is positive. Therefore, it is V plus dV. So V plus dV equal to, it is a multiple of 3 dimensions anyway, as we know. So it is changed dimension along x, changed dimension along y, changed dimension along z. X plus dx, y plus dy and z plus dz. And it is notionally placed as dx because the changes in along x direction is not very huge, because changes in length will be very minute as far as their deformations are concerned. Therefore, x plus dx into y plus dy and into z plus dz will be definitely changed volume, which can be expressed as v plus dv. And if you multiply this and this term, and yz will come, y into dz and dy into z will come, and there is also another term called dy into dz, which can be ignored because dy is too small and dz is also too small. Whenever two small things are multiplied, they become still small, like 0.2 into 0.2 is 0.04. So once again we multiply this, x into xyz plus x into zy, xy dz, like this. And here also we just ignore the terms like z into dx dy, y into dz dx, because of their small nature. Anyway, what we will remain with is xyz, xz into dy, yz into dx and xy into dz, after ignoring the multiples of small terms, because dx is a very small term. It's a piece of x. Dx is a piece of x, infinitesimally small piece of x, and so also dy and so also dz. So xyz plus, and we will rewrite this particular expression as, in place of v we will write x into y into z, because that happens to be the original volume, plus dv, change in the volume. And here again this expression gotten after expansion of this. So xyz and xyz will cancel away, leaving behind dv equal to xz into dy, yz into dx plus xy into dz, and dv will be this. Okay, and then we will divide all the terms by v, that is xyz. So this will become dv by v, xz dy by xyz. So x and z will cancel away. So we will get dy by y, dx by x and dz by z. So therefore what we get is the previous expression. What we get is dx dy by y, dx by x and dz by z. Dx by x is epsilon x, that is strain along x. Dy by y is epsilon y, that is strain along y. So also strain along z. So we will reduce, anyway it will boil down to volumetric strain equal to dx by x, dy by y and dz by z, as I said earlier, this can be replaced by epsilon x, strain exclusively along x direction, strain exclusively along y direction, and strain exclusively along z direction. Therefore we have proved that volumetric strain is sum of strains along x, y and z directions. And we will later on coming to understand that this is not simply arithmetic sum, it is actually algebraic sum, because here epsilon x and epsilon y and epsilon z is the net result of strain along x. Epsilon x is net result of strain along x. It is net result because in other directions there are stresses acting, and it will contribute for the increase in the strain or decrease in the strain depending upon the nature of the stress. Therefore there is always a Poisson's effect. Therefore we will just redefine this expression as volumetric strain is net strain along x, plus or minus net strain along y plus or minus net strain along z. So here is a body which is subjected to sigma x, sigma y and sigma z, and it is important to realize that the strains are net strains, as the strain along a particular direction is influenced by the stresses acting in other directions simply because of Poisson's effect. Now epsilon x is, so we will try to calculate epsilon x for this body. So this is sigma x divided by E. So this is called as primary strain. Primary strain that happens along x direction exclusively on account of sigma x, which is also acting along x direction. Now we will look into side effect. So there is sigma y acting in this fashion. So it is pulling the entire member and the entire component. So when it pulls, it becomes lengthier along this direction, but it becomes shorter along this particular direction. As far as sigma y is concerned, this is the changes that happen along x and can be called as side effect. So it is lambda, it is Poisson's ratio times whatever that happens along this particular direction. Yeah, it becomes small in that direction. So this can be accounted by an expression mu times sigma y by E. Sigma y by E is a strain along this particular direction. It can, and we are contemplating to find out the strain along this particular direction. So it is Poisson's ratio multiplied by this strain along this particular direction. This is longitudinal strain as far as sigma y is concerned along this direction. But the lateral strain is the strain that happens along x. Since it is a tensile stress, it is going to reduce, while sigma x is trying to increase the dimensions along x direction. Sigma y is not contributing for the increase in the dimensions along x direction. Therefore negative sign comes into picture. And similar thing will happen to sigma z also. Due to sigma z, which is a tensile stress, the dimensions along x will be reduced, and that is equal to minus mu sigma z divided by E. We can hold the same argument and we can extend the same argument, and we can just develop an expression for net strain along y, which is something like this. And my respected viewers can write a sketch and they can visualize why this is to be minus and why this is to be minus. In general, if you consider strain along a particular direction, and if the stresses along other direction happens to be tensile, it's going to reduce. That is for a reduction. Elongation in one side will always be associated with contraction on the other side, or reduction in dimensions on the other side. And similarly, epsilon z is the primary strain along z direction, that is sigma z divided by E, minus secondary effects due to Poisson's effect. So therefore we have arrived at net strain along x, net strain along y, net strain along z, and we have proved that a volumetric strain is epsilon x plus epsilon y plus epsilon z. This is called as, these equations in general are called as, that is 1, the net strain along x, net strain along y, net strain along z, are conjointly called as generalized Hooke's law. And simple Hooke's law happens to be associated with only one unidirectional stress. Okay, and that is stress is proportional to strain. That's what we argued. And here, whenever you consider a component which is acted upon by stress in three mutually perpendicular direction, side effect is to be accounted, and the equation is much more than sigma x proportional to epsilon. That is, stress is proportional to strain. Stress is also proportional to the strains that happens due to the stresses acting in some other direction. That is the meaning. That is what we call it as generalization. So epsilon v, this is net strain along x direction plus net strain along y direction plus net strain along z direction. And if we simplify this, and if we take out 1 by E as a common factor, sigma x comes here, sigma y and sigma z, they are all positive. And if you take minus as the common factor, and mu and mu by E, and here you can see mu times sigma y by E, and here again there is mu times sigma y by E. Therefore we will get 2 mu times sigma y divided by E. Similarly we will also get for 2 sigma x mu divided by E. Okay, therefore we will separate 2 mu by E as a common factor, and we will once again get a factor sigma x plus sigma y plus sigma z. Once again we can take the common factor as sigma x plus sigma y plus sigma z divided by E as the common factor, and what remains in the brackets is 1 minus 2 mu, 1 minus 2 mu. And in some cases, in specialized situations, like an element within the body of water, like an element within the body of soil and under great depths, and this particular element will be experiencing same magnitude of sigma x and same magnitude of sigma y and sigma z, and such a situation wherein the stresses along mutually 3 perpendicular directions happens to be same, such a stress is called as spherical stress. So this is a special situation of sigma x becoming equal to sigma y and sigma z, and this is typically called as volumetric stress. So in order to call a stress to be volumetric stress, it is essential that it should be equal in all the 3 fundamental directions, and that situations in reality, in the real world, appears only for elements which are hidden in the fathoms of soil and in the fathoms of water. So, and if you add this will become 3 sigma v, and we will change the notation as sigma v, or 3 times sigma v divided by E into 1 minus 2 mu. So this is a famous expression for epsilon v, that is volumetric strain in terms of volumetric stress and modulus of elasticity and Poisson's ratio. Therefore volumetric volumetric strain happens to be a function of volumetric stress or spherical stress, modulus of elasticity and Poisson's ratio. So within elastic limits, we can extend the Hooke's law for this spherical stress and volumetric strain also. Within elastic limits, the spherical stress is proportional to volumetric strain. We will write this in the form of a notation. So sigma v is proportional to epsilon v, and if we remove this proportionality symbol, we will get sigma v equal to k times epsilon v, and this k is what is called as modulus of bulk, or bulk modulus of bulk changes. Okay, because this will connote overall changes in a body under elastic limits, because it accounts all the 3-dimensional directions, and it connotes changes in the volume, and it is a measure of change in the volume. Therefore it is called as modulus of elasticity. More modulus of elasticity is there for a particular material, more elastic it is in all the 3 fundamental directions. Okay, K is bulk modulus or volume modulus or dilation modulus. Okay, because it connotes, once again I repeat, it connotes the capability of material to undergo volumetric changes. It is also expressed in MPa. So we will take an illustrative problem of an element, rectangular element, which is subjected to stresses in 3 mutually perpendicular directions. E is given to us, and Poisson's ratio is given. This is for a better way of understanding how exactly the net strains could be calculated. And the thing is, we need to find the change in volume. We will also see whether it is positive or negative, whether it is going for reduction in volume or increase in the volume, right? And sigma x, the basic strain is, if you go this, sigma x is 500 kilonewton divided by area. Area is 400 by 500. Yeah, that's what it is written over here, and it is 2.5 MPa. Similarly, we calculate sigma x. Looking into the figure, it is 600 into 10 to the power of 3 acting along y, and the area of cross section perpendicular to this axis is 400 into 300, so we get 5 MPa, and once again sigma z is 400 into 10 to the power of 3, and this is compressive. Actually this should be given minus sign, This is for reduction. Sigma x is for the reduction of the dimensions along z direction. So we will calculate the net strain by considering individual forces, and 500 kilonewton will create primary strain along x direction. Therefore we will write it out first. Epsilon x is sigma x divided by E, and as far as y directional stress is concerned, that is also for the, it is tension, therefore it causes a decrease in this particular direction. Therefore what is the percentage of decrease? It is mu times sigma y by E, and sigma y by E happens to be the primary strain along y direction. We are not worried about primary strain along y direction, and we are just calculating the algebraic sum of the strains happening okay, along x direction due to stresses in some other direction. Okay, and similarly sigma z is compressive, and here is a very important point. Sigma z is compressive, therefore it will create bulging along x direction. It will create increased dimension along x direction. Therefore anyway, it's a side effect as far as sigma z is concerned. The changes that happen due to sigma z along x direction happens to be the side effect. How much effect is this? It is mu times the effect along z direction. In the same token, we calculate this 2.5 divided by, we have already calculated sigma x and sigma y and sigma z, and we will substitute that only to get back what is epsilon x. Net strain along x direction is this much, and epsilon y in the same way, that is also tension, therefore 5 over 200 into 10 to the power of 3, and this is minus, this is not contributing. Okay, the stress along x is not contributing because that is also tension, plus anyway the stress along z is contributing for the increase in the dimension along y, therefore it becomes positive. Therefore net strain along y is 2.528 into 10 to the power of minus 5 upon simplification. In the same token, if you calculate for epsilon z, that is net strain along z, it is the primary strain along z. You can notice minus sign appearing because that leads to decrease in the dimensions along z direction, while the tensile stress over here acting vertically up will also contribute for the decrease in the direction, and the tensile stress acting along x, that is also for decrease in the dimensions along z. Therefore everything will become minus 5 over 200 by 10 to the power of 3. This is due to owing to sigma z, and this is owing to sigma x, and we will get epsilon x, that epsilon z, that is strain along z direction. Net strain, I hasten to add this, net strain along z is minus 2.572 into 10 to the power of minus 5. If we add it together, what we get is volumetric strain is algebraic sum of strains along three directions. So this is along x direction, this is net strain along y direction, this is net strain along z direction, and what we get is 8.21 into 10 to the power of minus 6. Now we have been asked to calculate change in volume dV, because dV by V equal to epsilon V. We need to calculate dV, therefore dV equal to epsilon V into V. So epsilon V, we will substitute this particular value into V is the multiple of all the three dimensions. So along x it is 300, along y it is 500, along z it is 400. We multiply everything. This is the original volume, and this is the strain, volumetric strain. So what we get is 492.63, which is a positive value. This positive value connotes that there is an increase in the volume. Of course 492.63 millimeter cube is nothing. It is a very timid quantity, but however, in order to cause such a change, huge stresses are involved. That is the point of concern, and that is the gist of our discussion. So in this tutorial we come to know as to what volumetric strain is, and how to calculate volumetric strain, and how to define bulk modulus, and we have exemplified with a typical example, and we have understood how to calculate change in volume or changed volume, and therefore we can also calculate bulk modulus. So with this we will conclude our tutorial session, and in the next tutorial we are going to come out with the advanced portion of this volume changes, etc. Until then, bye. If you have liked this video, kindly subscribe to my channel.